Okay, welcome everyone to as it turns out, the last session last weekend of this series of runs. Uh, I may not be available next weekend and then it's tied up afterwards. So I guess in any way, logistically speaking, whatever topics I wanted to cover, I have kind of covered. We got enough. I mean, almost looking at 4 hours every weekend. We have already into the 20th hour now, 19th, 20th hour now. So it's almost like a half semester kind of uh, time that we have spent. So there is a lot of stuff that we have covered. So I just wanted to kind of take off from where we left off yesterday and show you 4 or 5 notebooks which talk about the applications of just this workflow of machine learning, deep learning applied to healthcare problems, just to give a flavor of how this works in practice. And then after the break, I just wanted to very briefly introduce the topic of medical prognosis and medical treatment. And towards the last 10-15 minutes, we'll kind of wind up. Uh, and then, of course, we will be hopefully on the same group so we can take offline questions as and when required. So I will not be covering graph nets and reinforcement learning because obviously there's no time, but I will cover whatever is targeted for this scheduled weekend. So let me just show you. So 4 or 5 notebooks is what I want to show. I have not uploaded this on the Google Drive. I will do that later today along with the videos of the last 2 sessions, including today's. Um, but I did show you the Mednist tutorial yesterday when we talked about how you can uh, try to classify the type of a medical image, whether it's a head CT or a chest X-ray or bone X-ray or whatever, and how it's easy to kind of train those kind of networks and make predictions. Today, I wanted to show you a logical next extension of that, which is uh, this notebook on bone age estimation. Uh, so some of the part of the notebook would be kind of code related, some of it could be data set related. So don't bother if you kind of not get the picture of, but I will try to at least go through some of the key concepts that I want to, and because I have to cover 4 to 5 notebooks in the next 40 minutes or so, I'll go about on an average spend 10 minutes per notebook, just to give you a flavor of how this works. So here is this data set of images, which was published by RSNA. RSNA is the Radiological Society of North America, which publishes a lot of work, um, a lot of data sets for a lot of medical diagnosis kind of problems. So this data set contains about 5,000 images of all males between 10 to 20 years of age. Uh, and the idea is each image is like 384 by 384 pixel wide. And the idea is, can you build a network? Can you build a neural network which will predict the bone age by looking at the development of the bones that you see in the hand X-ray? So I'll show you with one of the networks that we build this with. There's a standard architecture called VGG16, which is just a combination of lots of convolutional neural networks and then uh, rectified linear units, the way we were talking about. So here I'm kind of setting it up as training data and testing data. And if you look at the data set, it has about 5,000 images. It has an ID. It actually tells you bone age, which is this is in terms of months since birth. Then this variable which says that, which is supposed to be true because it's our database of all males. Then it has a path where the actual image is saved, and then the actual score that is predicted. Now this is not the predicted score. This is actually a score which is given by a very famous uh, test which is approved by FDA. So I'm not going to go into those tests, but there are standard mechanisms by which you can compute those scores. So So the Bonnet z-score is basically just the score um, matched. Now, if you look at the distribution of the age, because this is a data set you have not seen, so the first thing you would do is exploratory data analysis. So you could see that the age is around, like most of them are around 160 months. And if you look at their z-score also, it's very similar to that. And all of them are males. There is no data about females. So somebody may tell you that this data contains, or somebody may give you a data set and say that this data set only contains information about males or all information about only females. But it is your job as part of exploration to actually verify that it is indeed the case, and that you can do by quickly uh, looking at either the statistical spread of these variables or by just quickly plotting them as histograms. Then we split the data into training and validation. So now I'm having a data set where I'm splitting or whatever of those approximate 5,000 into 3,700 odd of images in training data. And I will do the validation of my mm, model that I build on the 1,000 odd images that I set aside here. Now, if you look at uh, the distribution, it seems fine. So this was a just that this was a problem where we used Keras, which is a part of the TensorFlow library, TensorFlow 2.0. I also have done using PyTorch. So I'm just giving you some both flavors. This was at the time when this was done, I used TensorFlow and Keras. Now, if you look at the data set, this is the kind of data set that you have. These are what are called as hand X-rays um, of all males who are between 10 to 20 years of age. So 10 to 20 is what, 120 to 240 months. And here is a random plot of some of those images. So along with the actual bone age that. So now this knowledge comes from from a medically well established fact that your bones mature as you grow, and the maturity of the bones can actually tell you the age of the bones, and in turn your chronological age also to a fairly good degree of detail. And the idea was, can we pick up that maturity that we talk about, which radiologists are trained to see in these images and figure out, but can we train a deep learning algorithm which can look at the same maturity and predict that this is actually the bone age of this particular subject? Now, the thing that you need to know is that what we are predicting here is not a class. We are actually predicting a number which could be anywhere between 120 to 240 months. So this is actually a regression task. But just because it's a regression task doesn't mean we can't use a neural network. We can use a neural network for sure. And VGG16 is one of those architectures which allows you to do that. Now you define some matrix for loss, which is basically, I'm defining it as mean absolute error, which is basically what is mean absolute error. So suppose 174 is the actual age, and let's say my model predicts 178, then mean absolute error is 4 months, 178 minus 174. Now suppose uh, my model on another subject, like this is 192 months, and for this subject it predicts the age as 187, for example, months. Then 187 minus 192 would be actually minus 5, and that's why we take the mean of the absolute error, and it would say the error is about 5 months. And that's a good way to measure, because it doesn't matter which side they lie on, as long as you can kind of pick up those errors. So here is a way of how you define that network, which has lots of convolutional layers and 2D convolutions and some of the other parameters. Then you set your parameters to basically say how many epochs you want to run it for, what are you going to do in the process. Here is a way TensorFlow Keras kind of plots the architecture, where it says you start with your input image, which you give here, then you pass it through this VGG16 model, and then you go through a bunch of steps till you reach eventually a dense layer which predicts, which is only one neuron, because it's only going to predict one number, which is the bone age. Now you start your training on the training data that we set aside, and then it will kind of tell you, first of all, you will see that this shows number of batches. So I'm running it for 15 epochs, but by number of batches is 157 because I've set my batch size uh, to 157, which was just basically computed as 5,000 divided by 32. So I wanted to give 32 images in one go every time because that was the hardware capability of my hardware at that time. I was not running this on even GPU. It was a simple CPU based machine. So the training involves presenting each batch data sequentially, and the epoch only ends when you're finished with 157 batches. So every time you will see 157, and this is generally a progress bar. So when you train this, you will see this equal to sign going from left to right, showing the progress. Eventually, it will start with 1 by 157, 2 by 157, and so on and so forth till it reaches 157. And at the end of the batch, it will compute the loss. It will compute the MAE, which is the mean absolute error loss in months. And it will also run the model, whatever that was trained on at that time, on the validation data set, which we set aside, which was the 1,000 odd images. And it reports the same two numbers for those two also. Now with one batch, you will get pretty bad numbers. So you kind of with one epoch you'll get bad numbers, so you kind of run it through multiple epochs. And as you go through this process, you will see that by the time you reach 15th epoch, your the error between the actual age versus the predicted age by my network has now kind of come down to 12 months, starting from 22 months, 23 months. So obviously it is training. I didn't run it. I could have run it for more epochs. It would have even come down to single digit. And then there is some code that I'm writing which shows how this is working on. And the idea is it's not only going to give you uh, the age. So here is an image, for example. On the left side is the hand image whose age is 17.5. This is in years. And then my model predicted it to be 15.9. And it also told me, so the bright things that you see here are the regions that it identified as the main bone areas that it used to compute this age. So these, according to the model, these are the regions which from this image, which led it to compute the maturity of the individual as so much, maturity of the bones as so much, which led to the chronological age. So this thing changes on every map. So for example, here it's a very young uh, child of 11 years, 11 and a half years. The model predicted the age to be 12.3 and essentially focused on only these part of the knuckles. And you can see different results. So now when you run this, when you run this on a validation set, what you see is a result which is shown as actual age versus predicted age. Remember, this is a regression task. This is not a classification task, so we are not going to show you any confusion matrix, etc. I'm going to show you a predicted line along with the red dots. Red dots are the ones which are the actual age versus the predicted age. So this is uh, how different the actual age looks like from my predicted age, and this blue line essentially shows the mean absolute error. And you can see that while there is a spread, obviously, because it may not have been trained fully well, it is uh, still doing a decent job. There was another model which is very popular, which is called Inception version 3 model, which is from Google. And if I run the whole thing on this, I'm not going to go through the full data here, but I will show you the end result. Um, and it's a different architecture, but the process is still the same. And when you do that and you predict it, you can see that the spread is a little different. The spread is different, and the way you are predicting the age is also different. So this is one way by which you can run your regression tasks on, let's say, a particular problem, which may even involve either an input data, which is an image, or an input data, which is, let's say, um, a tabular data like a CSV file or a Excel file, or even your genomic data, if you will. Anything is fine. It entirely depends on what you're predicting. it can predict. It can predict any number outside of the range also, because the error is so the mean absolute error is, as I told you, was for the model was about 12 on the training data, and it was I just closed the notebook, but it was about the 30 35 for the validation data, which essentially means that in the worst case I may have done uh, predicted 30 months earlier as the age. So if your training boundary is, let's say, 120 months, and if I'm predicting 90, that's possible because my model can predict that. If whether it will predict 40 or not is, if it starts predicting 40, then you know your error is not well managed, so your network training has not happened well. So those kind of conclusions that can help you steer your training to either a different architecture or tuning your hyperparameters in a little better way and kind of move forward. There's another notebook which I want to show you now, which is on the chest X-rays, which is predicting pneumonia. This is an example I've been giving, and this is kind of going to show you roughly how the convolutional neural networks work, because most of the imaging tasks use convolution because of the local proximity of the features uh, and things like that. So same assumptions on which we kind of decided that why convolution is a better model than MLP. Uh, all those are valid in case of an image data, so it works on image data well. So I'm going to show you this data set, which is called the CheckSNet data set. Uh, this was published by Stanford AIMI library, and it has a data which comprises of 14 classes. 14 different pathological conditions were diagnosed by people who are radiologists. So they looked at the chest X-ray. They said this pathological condition exists in this chest X-ray or not, and they indicated it as 0 and 1. So if you look at the data, it really shows you uh, the name of the files, of course. So this is, I'm just showing the first 5 rows here, but it has all the number of whatever number of data is there in the training data set. And then you can see the conditions here as cardiomegaly, consolidation, edema, effusion, each of fibrosis and all, each of them is a condition, and it is only indicated as 0 or 1, which essentially means radiologist basically predicted where whether there was edema in this patient or not, whether there was effusion seen in this particular patient or not, right? So you kind of run these models through some experts, get them to label the data. That's what we are doing here, and then kind of put that whole information into a data set. So this is what the data set is, and of course you will have a patient ID and the rest of the other conditions like pneumothorax and pneumonia and things like that. So there are totally 14 such conditions. Those 14 conditions are listed here. Now, the first thing you want to do is you don't want to. So what I mean by check for data leakage, right? So what the idea is, and this happens especially with medical data, you may get multiple images, multiple X-rays of the same patient, for example. It it could so happen that an X-ray was taken a week later, or what, and when you put this together in a data set and you kind of blindly split this into training and testing, it is possible that the same X-ray, I mean, by not same X-ray, I'm saying X-ray of the same patient, one image may lie in the training data set and one image may lie in the validation data set. And that's not nice, because then the network can just simply memorize how this particular patient's X-ray used to look like as a nonlinear function, and just go and see the same pattern available in the validation set and straight away say that whatever was the label for the first X-ray of this patient is the same label for this patient in the validation set. And that can actually trick your algorithm a lot. So the idea of data leakage is basically to ensure that you don't have same subject ID or patient ID in training as well as validation data set. You don't want that. So what you want to do is, so one way to do this is to basically, if somebody gives you train and validation set, you obviously go and verify this. But if somebody doesn't give you this, and if you get one large big monolith of a data set, then what you do is when you're splitting it, you split it on the subject ID basis, so that you are ensuring that the subject ID is not repeated in training versus validation. So you don't want the same data of a particular patient time different to be available in both training as well as validation data set. So that's something you want to avoid. So that's what this whole thing does. Then you kind of prepare the images, then you write your network. Um, these are just the standard workflows. I'm not even going to go into all of these things. Then you develop your model, and then the example that I was giving yesterday about class imbalance, right? Whenever you have an imbalanced class, your networks will tend to behave in a biased manner towards the class which is most predominantly available. Now you can see here for the 14 classes, if I plot it as a frequency, not as a count, but as a function, as a proportion of total number of patients, then you can see that this infiltration class is the one which takes, which seems to be predominantly available, whereas some of these classes are hardly even represented in the data set. So all the 14 data sets, 14 classes are not well represented in my training data set. So there is an imbalance. So if I run my network just as is on this, I'm not going to get good results, because my results should be primarily biased towards this class or the majority classes which are predominantly available versus the rest of the classes. And these may be the rare conditions that you want to pick up, for example. Then your training, then your network is not good enough after all, because you can't pick up the rare events. So the way you kind of do that is with through a bit of some kind of a jugglery. I'm not going to go into that jugglery, but basically you represent it in such a way that if your class distribution was like this for positive versus negative classes, so positive, what is positive versus negative? I mean, this label present versus this label absent. That's what it's a positive and negative. There is obviously, you can see a lot of class imbalance here. Now, now you can fix that by doing a bit of defining your loss function in a particular way, so that you can now see that you are getting an equal representation. The idea is not to make all, I mean, one way of class balancing is to say that you can actually have equal number of samples from each class. But the least you can do is this, where at least when for you're looking at positive samples versus negative sample, you have equal representation, which is what has been captured by this histogram. So you go about doing that, and you run your network then. And here I'm using this network, which is a predefined architecture called DenseNet 121, which has 121 layers in between, combination of convolution, ReLU, and many other layers. Now, if I were to run this and predict this, I'm not showing you the results of the training data and the prediction data here, but I'm just showing you the final result in terms of evaluation metric. And by the shape of this, you should know that this is now what we're looking at is an ROC curve. And what this is telling me is that for each of the class, obviously my ROC curve looks different because I have different number of uh, different grades of my network predicting those classes correctly, right? My accuracy or sensitivity or specificity for each of the class is different. The same model may have different sensitivity for different classes. And that's what is being picked up by this ROC curve. And what it really shows you is in comparison how these things work. And also what it shows you is cardiomegaly is the one which is detected best. And by just looking at the AOC, the area under the curve, you can kind of say which class is kind of getting uh, uh, well classified as. Now, you would do ROC analysis, and in any work that you do in classification, you will basically either do the computation of area under the curve or some of the other things, right? So this is something that you would do, and then you would compute, for example, your data based on what the radiologist said versus what your algorithm predicted, and then you kind of compute the difference between what the radiologist predicted versus what the algorithm predicted, and then you say whether there was any advantage in detecting a particular class to either algorithm or radiologist. Essentially, the advantage we mean here is the algorithm doing better or the radiologist doing better for that particular class of pathology that we are trying to detect in the chest X-ray. Now, there is a technique which obviously I don't have time to go into called GradCam, which allows you to see how your network is detecting and doing this thing. So I'll just show you an example here. For example, here is an image, a bunch of 5 images. This is an original image. This is showing that it has a cardiomegaly, but not very high. It's just showing it with 0.4%. Saying mass has this much probability of detection, and pneumothorax has this probability, and edema has this probability. Right. Now, with GradCam, you can actually show in the image which are the regions which the network thinks it used to compute uh, that particular probability. For example, you can see here that it is showing that it's this region that it is focusing on to compute the part of the mass. It is this region that it is focusing on here to predict that this has a high probability for mass. Whereas for pneumothorax, it was trying to focus on this part of the lungs uh, and some part of it here. Whereas for edema, it was not able to pick up very well, so it couldn't quite show. It was not even focusing on lung except for this particular part, and which can happen. Now look at another bunch of images and you can see how it tries to focus on different parts of the region and tries to explain. Now what this gives you as an insight, as an experimenter, is the fact that whether your algorithm is on the right path or not. Whether it is focusing on some of these tubes, for example, these catheters that you can see here, right? These are the ones. Now if your algorithm starts focusing on them and says that this is the reason why there is cardiomegaly, for example, then there is a problem. Then your network is not trained well. Either your network is not trained well or your architecture is not good enough for the problem. So you go back and check on multiple other parameters of training, the hyperparameters as they're called, figure out whether that is going to improve your training. If that also doesn't help you, then you go back and change your architecture. Change in the sense, not you don't make wholesale changes. You make small tweaks here and there and see whether adding a convolution layer makes your performance better. Adding a shortcut like a residual block in ResNet makes it a little better, or whether you need to change the number of filters in convolution, for example, to see whether the network will start training well now. Do you need to just run it longer, for example, and all kinds of things we can start concluding. And then you run through the process, see the results, and keep doing this iteratively till you reach a point where your results are comparable and in a form presentable. Right. So this is how you would kind of go through the cycle if you were doing a image analysis on chest X-rays. I'm not sure what is there in this notebook. Let me just open this. Oh yeah, of course. Let me show this also. So this is the evaluation of models. Now, remember I've been telling you that the most important thing that you do is, if you're doing a classification task, of course, is check your sensitivity analysis, your specificity analysis, your AU-ROC, your positive predictive value. You look at ROC, prevalence, accuracy, all of those things, right? So here is a notebook which shows that for the same data set, is looking at the same 14 conditions, pathological conditions, same data set that I showed before. But what I'm doing is I'm just kind of going through the process of training here and defining what are my true positives, false positives, true negatives, and false negatives. And then I'm going to write these functions and then compute them. And when I compute them, uh, I compare them with the actual Y, which is the actual label in the test data set, versus my predicted value. and then categorize that as whether it's a true positive or a true negative or whatever. So once I do that, I also have to choose a threshold, right? Because otherwise I won't know unless I'm doing an ROC. Now, when you do that, you can put all of this in kind of right in one bigger function, which I've called here as get performance matrix, for example, and it will tell me for each of the class what are the number of my true positives, true negatives, false positives, false negatives. What is the accuracy? What is the prevalence? What is the sensitivity? What is specificity? What is positive predictive value? What is negative predictive value? What is the area under the curve? And my F1 score, which is a, I've been telling you, is a harmonic mean of precision and recall. And then what threshold was used. Now, here I'm saying basically just computing these four things and nothing else right now. But then I can kind of write some other functions and then compute these things. And again, just defining these functions and then you talk about sensitivity and specificity and then define those functions to compute those things as well. And then you kind of run this function again. Then maybe you can kind of compute accuracy, prevalence, sensitivity, and specificity and show that data here. And then you continue going forward doing this for positive predictive value, negative predictive value, and compute them as well. And then compute the AUC. Now to compute the AUC, you need to know the ROC curve. So you plot the ROC curve, the same one that I showed you in the last notebook, uh, and then note down those areas under the curve as a fraction between 0 to 1. And then once you have all of these, you can of course compute the confidence interval and precision and recall. Precision and recall also you can plot as a curve, but based on that you can compute the F1. Now the idea, what is the idea of doing all this, right? So the idea of doing all this is depending on the problem that you're looking at. This can give you an overall view. This because there are 14 classes here. This can give you an overall view of whether your algorithm is doing well, whether its sensitivity is fine, whether its specificity is fine. Could it be increased? Could it be, or does it is it going to kind of suffer because of the threshold that I choose? Um, how what is the positive predictive? Positive predictive value is the label is positive, and you also predict that it is positive. Is that correct? Is that a good number for each class? You can obviously see that it turns out to be pretty bad for some of the classes, but it is good for some of the other classes. And then you can do a full-fledged analysis. So any um seriously technical work that you come across, whether you are doing it yourself or reading a paper or whatever, or even a blog post, will talk of a very detailed analysis and evaluation of the algorithm, and which primarily comprises of uh, confusion matrix and ROC values and these basic parameters. In fact, it is said that when you are setting up your design, right, you make, and by design, I mean design of solving a particular problem. And you obviously have to make assumptions in real life. You don't get data for everything. So what you do is you kind of make assumptions, you note those assumptions down, and then say that at a back of the envelope level, you do some kind of sensitivity analysis. It is recommended that you do this every time you go through, start from the process at the very beginning. What is sensitivity analysis? I mean here is uh, for whatever values you have assumed, for example, you kind of say, you take the worst case scenarios and compute the sensitivity and see whether your algorithm is or your model or your analysis is too sensitive to that particular assumption or not. If it is too sensitive, then you may want to change that assumption and try to get more data if required. So sensitivity analysis is part of a standard research process, generally called as study designs. And this way of computing it and looking at models will help you just follow that process of overall study designs so that you can kind of eventually propose a model which seems to by far work the best under available circumstances, under the assumptions that you make for the data set that you have been given. Yeah. So yeah, nothing else in this. Yeah, sure. So let me show you a couple of other notebooks if I can. Yeah. let me show you this one. Now I showed you how you can use images and convolutional neural networks in them. Uh, while talking about the architectures last weekend, when we were or was it last weekend? Yeah, it was last weekend. We were talking about how you kind of move away from the MLP kind of MLP is the uh, perceptron, multi-layer perceptron, to how you kind of look at the localized features and only focus on convolutional. And then if your data happens to be not just images, but some kind of a time series data or a longitudinal data, as it is called many times, then you may also want to have some kind of memory, because it's possible that your signal in the immediate past has some information which is useful in the value that you are predicting. Now, one of the signals that is very time series kinds is the ECG. And while talking of the architectures, I talked about how you can use recurrent neural networks or autoencoders or LSTMs for the analysis. That time it was a little theoretical. I will just show you now how you can actually use an autoencoder to analyze ECG beats, for example. So again, I'm not going to go into too much of the stuff about the data part, about the notebook as such, but I'll just show you what the data is kind of consisting of. It's like a time series data of every patient ECG, which is kind of recorded as a numerical array. So I'm not working with any images as such, but I'm just looking at the data. Now, if I look at, if I plot the uh, labels, what it says is there are 5 pathological conditions. I'm not very sure of what each of the precise definition of each of them, but I think it is there somewhere in the notebook, or it is, you can find it out in any case. But just for now, assume that there are 5 different pathological conditions that you are trying to detect in an ECG. And again, your labels are like this. Your majority of the ECGs are normal, but there are 4 conditions that you see here. And the way we are, so now what you do is you try to take the peculiarity complex. So because considering its sampling frequency, etc., we are basically showing about 150 samples here, which kind of constitutes one PQRST complex of the ECG, so one beat. So if you look at the normal uh, ECG, it has a profile like this, and what you see as the light blue color around is the 2 standard deviation uh, around the mean, also plotted, so that you know the rough variation of the data. And what you can see very easily here is that for the rest of the 4 conditions, you can actually see the anomaly. You don't see this P wave very clearly, which you see in the normal profile. You don't see it here in any of these 4 conditions. And now the idea is you don't have a physician who's going to look at this ECG and classify it to you that this is normal or this is abnormal. So you don't have any label data. So if you don't have access to a physician and you don't have label data, what are you going to do? You can't just give up. So these are the times when you kind of use some of these techniques called as the unsupervised learning techniques, where you don't use any label data and try to extract any pattern or features that you see in the data set yourself. So what we are now going to do is showing you I'm going to show you an example of an autoencoder architecture, which will be trained on normal images like this. And then what it will basically do is try to see if this pattern exists in any of these conditions also. And if it doesn't find it, it is going to call it an anomalous ECG. So it's going to classify ECGs as normal versus anomalous, normal versus abnormal, without knowing anything about them, by simply looking for this kind of profile, which is there predominant in the normal ECGs. And if it is absent in the others, then it will going to flag them off like that. So that's the plan in this notebook. So you define your encoder and decoder as the 2 elements of your autoencoder, and then the bottleneck part that we define as on the autoencoder. So here I'm just defining that part. I'm not going to go into all of this. So if you now kind of look at the training loss, I run it only for 8 epochs, and you can see that the blue curve is for the loss on the training data, and the yellow one is for the testing data. And you can already see that my losses kind of start dropping very quickly, very soon. And then what I do is I kind of plot this. So what I'm plotting here is the normal loss, the normal, sorry, the first row shows the four ECGs which are normal, and the second row shows all the four ECGs which are abnormal, or whether they have some kind of anomaly. And you can see that the loss is high in anomalous conditions more than in normal conditions in all the four cases. And then you actually use that as a threshold to predict what your uh, what your uh, prediction is going to be. So this is one way by which you can use an autoencoder kind of a circuit, or an autoencoder kind of an architecture in a deep learning network where you don't even have label data. So the way you can try to do is, if you know that you have sufficient amount of normal samples, here we're talking about ECG, but it could be for anything else, then there will be some signature, or what many times people call as biomarkers, in the signal itself. And then you you try to encode that signature part in your encoder, and then try to see if that is present in another image. If it is present, then you say it's a normal ECG. If it is not, then you say it's an abnormal ECG. Here, no physician gave you a label saying that this is normal, this is abnormal. So this is another way in which you can use these kind of information. And as we come close to the break, I want to show you one last notebook if I can. Yeah, I'll show you this one on this example from dermatology where you're trying to kind of detect skin lesions. Now, what is the idea behind me showing you different applications is, of course, one that uh, it can be it can work on many of the data sets, but also to give you an idea that eventually what you do is essentially the same thing. You kind of decide for some kind of an architecture, and then using that architecture you kind of start detecting whether a particular condition is there or not, whether you are detecting the bone age, whether you are detecting whether there is a pathological condition in a chest X-ray, or whether you are detecting pigmented lesions on skin on dermatoscopic images. Anything is still the same. So I'm using one of the Kaggle data sets here. So again, I will not, I'll leave it for this. I'm going to upload all these notebooks, so you might actually spend some time reading them offline if you will. But essentially, I'm going to show you some sample images here. So the sample images are of some kind of skin lesion for different conditions. So as you can see here, these are the, I have somewhere listed them, yeah. So these are the coded names for the conditions that have been, for which the data has been collected. And you can see that they kind of have a very similar profile when you look at a class of them together. And the idea now is, can you train a convolutional neural network? Because here I already know the labels, right? I already know what is BCC, what is NV and all that. So I already have the labels. So I don't need to do autoencoder and things like that. So can I come up with some kind of a convolutional neural network, or some kind of a ResNet kind of an architecture, or a DenseNet kind of an architecture, which is standard off the shelf architecture, and try to train it on this data set and see if I can predict, uh, if I can train the model so that it can predict on an image it has not seen. For example, the idea is, if we eventually give, after training our network this image and don't tell it is male, do we do we do we see that the model is actually predicting a melanoma? So so that's how you kind of set up your problems in healthcare for solving using networks. So here I'm showing an example with ResNet 34. So that's the architecture here of the network. Uh, it's fairly big, so let me just show you in any case. So it has a bunch of convolutional layers and basic blocks, as it calls it, a lot of them actually. So it's a full-blown 34-layer network. And then what we are going to do is we are going to compute the training loss, validation loss, and compute the error. And when you do that, what you do is what I'm showing you here is the predictions that the model that I just trained with is showing. So what so the legend is really the first thing is the predicted label slash actual slash loss slash probability, which basically means the original label was melanoma. My model predicted NV. Loss is about 5.53 and with zero probability. 0.00 means not zero probability. It must be some 0.0030. It must be a very small very small probability. Um, there are some places where it gets it right. There are some places where it doesn't get it right. These are all the examples where it doesn't get it right. Then I can show you some other examples, but with a heat map. Now, what is this heat map? The heat map is again the same concept of GradCam that I told you, that I showed you in the chest X-ray image, where it kind of tries to focus on which part of the image it focused on to tell whether it is how did it find this. So look at this image. It has what it is telling me is that it is focused on this region of the image to come up with this prediction. So clearly, it has not focused on the wrong part of the image to predict this. Right? Look at the second one image immediately below that, and you can see that it is trying to indicate that it has picked up the same region that it needs to focus on. So it's focusing on the right regions, but it may be still getting the labels wrong. Then that's perfectly fine. Then it's just a matter of fine tuning your model well. So here is a confusion matrix. Confusion matrix is, as I told you, is a number of classes. The size of the matrix depends on the number of classes. So here we are predicting how many 7 classes. So it's going to be a 7 by 7 matrix, and you typically have the diagonal entries well predicted, and then you fine tune your resonate if you require, and then you get some next level of confusion matrix, which seems to show that it is doing better than the previous time, and you go on experimenting this. And this is also another reason, now we are on the last session, so I can make this point, which I had made on the first day, as to why you should use Jupyter notebooks for research when you are dealing with data science. So now you can see that data science is primarily an experimental science. And this is more like a journal that you keep a record of all the things that you do. So imagine you opening this notebook. I'm opening this notebook after like a couple of years, maybe, or or maybe almost like a year at least later than when I created it. And I'm not going to remember everything, right? But if I keep it, if I write it down in such a way that it has a particular flow, they can always go back to the entire history in the notebook and kind of figure out what I was trying to do and what I was able to achieve. So that's how you kind of keep your practicals, journals, records as a scientist. And because this is experimental science at its core, I suggest using notebooks is probably going to make your life much more easier than you trying to write this into some notebook and then you kind of lose that notebook, or that notebook gets failed, you move to another notebook, and then you don't have access to the previous one, and all kinds of things happen. So, which is one of the reasons why I strongly recommend people use Jupyter notebooks for their work. So I showed you so far an example of ResNet 34. Now I'm going to show you an example of ResNet 30. Yeah, so what I'm showing you here, I just saw your message on the chat. So what I'm saying here is, if I can go back to that image, this is after learning. This is not, I am telling it. I just simply gave these images as of training as an input, bunch of them together. And then it picked up, for example, for this image, that this was the region. It learned that it needs to focus on this region to figure out its class. Maybe it got the class wrong, but at least it has focused on the right region. So I'm making two statements which may have confused you. So what it is showing is the result of training. So this is after training, and this is what the network, the neural network actually was trained to focus on. And the second part that I'm making is the point of interpretation, where I'm saying that by looking at this, you can actually say that it is focusing on the right region, but those are not the same part of the same coin. So one part, the region is computed as the region that it focused on by its training, and the second part is the interpretation that I'm talking about here. Yeah, good point. So it goes on like that. So I think it's also, there's nothing else that I wanted to show you in this notebook. Yeah, it's a little bigger notebook, so I'll kind of stop this here as well. So I think it's also time for our break. These are the kind of notebooks that I wanted to show you, which kind of give you an idea of how you can use same workflow to kind of, what changes is your data set that that is coming from, and what changes is the problem you are trying to solve, whether you're trying to find the bone age, or whether you're trying to detect pneumonia in X-ray, or whether you're trying to detect skin lesions in an image, or whether you're trying to detect if the ECG rhythm is normal or abnormal. The data set changes, your workflow remains the same, and then you kind of get some predictions from your network. And then your job is really, as a data scientist, is to analyze and make sense of those evaluation matrix and make a case as to whether the model that you have now got trained is good enough, or bad. And accordingly, then you make choices as to whether you need to go and collect more data, or whether this is all as good as it can get. So those are the kind of activities that you would do as a practicing scientist, but that's the typical workflow. So it's almost 4, so I'll take a 5-minute break, maybe not 10 today, and we'll see you back at 4 or 5 for the other part, in which we'll kind of talk about a problem we have not spoken till now, uh, and then towards the end we'll kind of wrap up. So I'm going to pause the recording. Hello everyone. Then on to the next part, which is actually, and I'm talking about medical prognosis and medical treatment, is, you might be just wondering what do I mean by them? But just to give a context, I mean, each of them can be topics which can go on for another 5 weekends each. So there is enough and more still to be covered despite the 5 weekends that we have done. But I thought at least I'll give you an idea of a very high level idea of what those problems are, and maybe if you're interested, you can go and read up about them, or maybe we could, who knows, maybe a couple of months later, maybe we could do some kind of a session again. So what is medical prognosis? So prognosis is a term which is used often in medical literature and healthcare, which refers to predicting the risk of a future event. Now, what have we done till now in these 5 weeks? All right, if you look at the 5 notebooks that I showed you, or for that matter, even many of the tasks that we were talking about, they kind of primarily about detection, right? Detection or diagnosis. You're trying to detect if a viral pneumonia exists. You're trying to detect if the ECG is normal. You're trying to detect if the bones are mature. You're trying to detect if there is a skin lesion present. So those are the kind of problems which you focus on diagnosis, and majority of the work in AI and machine learning in healthcare has primarily been done on the diagnosis side. But there is fascinating scope for it in the other two later stages of that, which are prognosis and treatment. So the idea is this: let's say from whatever we did so far, we built a network or whatever, which was trying to predict, which was trying to detect or diagnose that a particular condition exists. Once you know that, then the next step is to predict what is the risk of an event. For example, if your ECG is, let's say, not normal, abnormal, what is the risk that you are likely to have, you as in the patient is likely to have a heart attack or a stroke or even death? And these kind of analysis are often done in hospitals, in even in individual cases, because you want to estimate whether there is a potential risk to the patient all the time if they show some underlying medical condition. And you'll be surprised that machine learning is actually a very powerful tool for prognosis, because what is prognosis at the end? If you focus on this word, predicting the risk of future event, that's essentially what we were trying to do in the uh, diagnosis phase also, right? We were trying to train it based on the retrospective data, and then for some kind of a prospective event, we're trying to predict. So that kind of fits into our normal workflow of what machine learning is. And that's essentially what we're trying to do here as well. So machine learning can actually be a very powerful tool in making predictions. But what you need to do here differently is you need to combine many other forms of data. So you may have lab events, lab reports, you may have handwritten notes. Again, all of those stuff comes into play again. How is this useful in clinical use? For example, you can use it to inform patients about the risk of developing an illness, right? For example, you may estimate the risk of a person developing cancer by doing a few blood tests. You may just forewarn a person to be careful. You can estimate the risk of diabetes, for example, and maybe advise the patient to take some corrective steps now itself so that there is no onset of diabetes. Another way in which prognosis is useful is you can inform patients how long they can expect to survive if they have a certain illness. And this is the standard staging that is used in many medical conditions or cancer staging. We say the patient is in stage 1, 2, 3, 4, 5. 5 is generally mortality. There is COPD, which is lung related. That also goes through different stages 1, 2, 3, 4. Uh, and what it allows you to do is you don't have to specifically tell a person that you have only 2 years on your hand or whatever. You tell them that they're in stage 3, they kind of can imply uh, the underlying message. The third thing that prognosis actually helps you do is it's kind of a connect between diagnosis and treating a disease. So if you look at the larger goal of healthcare, right, you want to first detect if there is a condition. Then you want to predict what is the risk of that patient developing a future event. And the third is, of course, you're going to treat that patient with something else. And it obviously helps you in assists you in uh, the stage of medical treatment. So the idea is this. Typically, what happens in prognosis is you have a profile, and profile kind of typically comprises of clinical history. It could contain a physical examination. It could involve lab reports and imaging data or whatever. All of that constitutes a profile of a patient, and this can be longitudinal. It can be captured over a period of time. And then what typically is done in prognosis is you build some kind of a model. And I'm using the word model in a very in a very liberal way here. I don't necessarily mean machine learning model, but you can build some kind of a prognosis model which can give you a risk score. Now that risk score can be given as a number, for example, like 121, or it could be given as a percentage risk, like you have a 21% risk or whatever.
अच्छा आपको जाने पड़ा अभी?
So now this prognosis model is uh, is the one where you can focus on. If you are coming from a data science background, you kind of think of, first you need to read up literature on how it's currently done, and then maybe kind of build a network here, just build a neural network in between here so that you can build a network which gives you a risk score by looking at a particular profile. And then what you would have built is a prognosis model and not a diagnostic model. So diagnostic model is one part of the problem, but prognostic models are the ones which are going to be useful to the patient in genuinely improving their healthcare. Today, if you look at the literature, there are many different scores that are given. For artificial fibrillation, there is something called as Chadsbach score. For liver disease mortality, there is a MELD score. For risk assessing the risk of a heart disease, there is an ASCVD score, ASCVD score, and there are for almost every condition which can lead to a future event like stroke or whatever. Uh, there is a score, and these scores are computed using a very simple tabular way. You are these are so what you see here as these acronyms, they actually stand for certain conditions. So whether you have diabetic, whether you are hypertensive, is your age greater than 75, those kind of things. So you give plus one for those things, and then eventually you get a score which is like out of some 10 or 20 or whatever. And the higher the score, so if you're kind of looking at two patients, the one with a higher score obviously has a higher risk of developing this future event. Now, the idea is, can we build a model, which is a machine learning model, which can do these kind of things, not in the way traditionally it's done, but by looking at the profile and extracting data and things like that. So how do you evaluate prognostic models? Their basic idea is to see how well they perform on pairs of patients. So what you do is you take a patient A, you take a patient B, and let's say we are looking at a future event of, let's say they were diagnosed and treated with something. And from that point onwards, for 10 years, you observed whether that particular patient was survived or could not make it. So yes and no. And then you assign a risk score. And the general idea is that a good prognostic model is the one which gives you good score, a higher score for this kind of patient A who survived the event, than for the one who could not. So, so whether you are learning this through a neural network, or whether you are learning this from the data, or whether you are taking it from the literature as is, your risk scores should at least have this kind of trend, that patients who make it, who don't have that event, generally have a higher score. Now, based on this notion, there are quite a few things. Just as we had the notions of in confusion matrix, we had the whole scheme of things where we computed sensitivity, specificity, accuracy, precision, recall, and all that. Similarly, in this kind of case, there are few possibilities, right? You're talking of two patients because we are looking at pair of patients. Now, what are can this possible? One thing that is possible is whether they had an event or they didn't have an event. So both yes, one yes, one no, or both no. That is one possibility. And then you could have a patient who had an event whose score is lower, or a patient who had an event but whose score was higher. These are the kind of possibilities that emerge out of this kind of a restricted setup, right? So you kind of give different names to these conditions. So we call them concordant versus non-concordant uh, pairs. We don't call them discordant pairs because it will be very clear why they are not called that and just non-concordant. So what is a concordant pair? So I'm giving you an example here in this left side top chart here. One of the patients had an event. So that is the first condition that they have to be that you are even assessing this for. And then the patient who had an event must have a risk score lower than the risk score for the patient who did not have an event. And that kind of a pair is called concordant. Discordant or a non-concordant pair is the one where uh, the score is higher for a patient who had the event. And the reason why it's not called discordant is for this reason. You may actually have scores which are tied. You may have one of them who had the event, the other didn't have the event, but they both had the same score. So this is also possible. That's why we just classify them as concordant versus non-concordant. And from this, traditionally what is done in prognosis is you compute what is called as a C index, which is basically concordance index. And there's a way by which you can do that. I'm not going to go into the details of this, but the idea is that uh, you take a bunch of patients, you record whether they had any event in the future or not. And when I say record in the future, record whether they had an event in the future, essentially means we are looking beyond the time when that event happened. So for us, for those who are doing analysis, this is still a retrospective data. So we are looking at somebody who was given a treatment 15 years ago, and we observed whether that person had a cardiac event in the 10 years after that. But because we are seeing it only 5 years later now, it still is a retrospective data for us. So what we do is we basically, to compute this Harrell's index, what is normally done is I'll come to that. That's the challenging part in prognosis. So I will just come, maybe in a couple of slides, I will answer hopefully your question. So I'm just trying to now tell you, if you collect this kind of data and if it is available, because a lot of times what happens is hospitals do monitor the patients. So maybe somebody had a surgery or a bypass or whatever, and they are obviously observed over a period of time. So the assumption is that when we put this kind of data set together, we know we have been observing that patient. That's an assumption. I'll come to the question when that assumption is not valid. But then what we do is we first find out what are the permissible pairs, as it is called, then find out how many of them are concordant pairs or non-concordant pairs. Then we count if there are any risks ties, and then there is a formula by which you can compute the C index as the number of times the number of concordant pairs plus zero 0.5 times ties divided by total number of permissible pairs. And here I'm just giving an example just to tell you what is a permissible pair. And so for example, what is a permissible pair? When I say AB is a permissible pair, but not AC, what do I mean? You can see the differences between AB and AC. The event occurred for B. The event occurred for A and not for the other. And that's how we look at a permissible pair. The permissible pairs are always evaluated in such a way that one of them had an event and the other didn't. But if I look at AC, both of them had the event. So it's not permissible pair. Both know, for example, BE is also not a valid permissible pair. So you kind of list down what are all your permissible pairs here. Then out of that, you find out which are the concordant pairs. And you remember the definition of concordant pairs. So let's say if I look at AB, I say AB is permissible pair because one had the event, one didn't. Then the next thing I do is I go and look at the risk score. And I see that the person who had the event had a higher risk score compared to the one who didn't. So this is a concordant pair. And that way I kind of list down all my concordant pairs. And I also note down if there are any risk ties. And there is a tie here at one place where the risk is 0.62 for the pair CE. And then I compute that in for this data set of 5 patients, my C index is 0.75. So there is a whole lot of literature on what this means and what are you supposed to do about this thing. But I'm just giving you a mechanism of a traditional approach where people use C index computations to kind of compute the possibility of a future event. Now coming to the question that was asked as to how can we observe the event. Even before I go to the point of whether we talk about whether the event is observed or not, there is this problem of missing data, and that's a problem which is there at large in any domain. It's especially problematic in healthcare because you are dealing with patient care and you don't want your missing data to kind of lead you to wrong conclusions or wrong path. Typically typically in literature, you will see these terms often mentioned. I mean, you will see, um, for example, if you read papers on some of the approaches, new approaches which are getting published in Lancet or Nature or British Medical Journal or New England Journal of Medicine or JAMA, Journal of American Medical Association. So almost all of them will talk about missing data characterized as either one of these three. One is called as missing completely at random. Second is called missing at random. And third is called missing not at random. Now, this terminology may look a little confusing at the outset, but let me give you with an example. Let's say you have a situation where a patient is walking in to record their BP. Patient, not a patient, let's say a situation where you are kind of set up a camp, let's say in a village, and hundreds of patients are walking in, and the job is to kind of record everybody's blood pressure. And let's say the person who's supposed to take this blood pressure tosses a coin. He or she tosses a coin only if head comes. He or she decides to take the record the BP. Otherwise, you don't record the BP. I mean, you don't know this because you're looking at this data retrospectively, so you can't control what had happened in the past. All you get is a data. All you get is a data, for example, of 100 patients where for for 75 or 80 BP recordings exist, for 20 it doesn't. Now, is that data missing completely at random, or missing at random, or missing not at random? Can actually tell you the causal relationship, which is why this is very useful. This kind of classification is useful. So when a person is just randomly uh, tossing a coin and deciding whether to record that particular patient's blood pressure or not, that is something called as missing completely at random. So you will have uniformity of patients with BP missing and with BP not missing. So there is no, there's no logic. It is completely driven by some random event, which was, let's say, a toss of a coin that the person at the counter was using. Let's look at a slight variant of this scenario and talk of missing at random. When we talk of missing at random, we say that he or she decided to take the recording for all those patients who were above 50, no exceptions. So you see the data of 100 patients afterwards, and you figure out that beyond a particular age, if the patient is beyond a particular age, then every person's BP is available. But if the age was less than 50, then maybe the patient at the counter was, I mean, not the patient, the person at the counter was tossing a coin and deciding whether to take the recording or not take the recording. So, so you see some kind of stratification that for a particular age profile, all data is available, and for another range of age, it is quote unquote completely at random. But it is only in specific profiles, which is why it's called missing at random. So this is the difference between missing at random versus missing completely at random. There is some hidden variable of which decides whether the data is going to be random here or not. If you are lucky, you will have that data, that hidden variable also somewhere in the data set. For example, age less than 50. But let's say there was some other variable. Let's say this person was deciding based on whether the patient was carrying some kind of an ID or not. Based on that, if that person was deciding that he or she should take the BP reading or not. Now, how do you do that? Because you're not, the data set is not actually recording whether the ID was there or not present. That's a variable which you don't have access to see now. But that variable was used to come up with this randomness. So it's missing at random. It's not completely at random. It is missing at random. And some of these hidden variables are also called as confounders. And you will hear this term a lot in statistics, biostatistics, uh, machine learning, the causal inferencing, that we always talk about confounders. Confounders are those variables which are hidden, which cause a particular event to happen, but you can't observe it yourself. And in the third category, which is missing not at random. And what is that supposed to do? So this is the third case, which I actually gave you an example of when I talked about the ID being available or not available, right? So other outside of that, the another confounding variable could be instead of an ID, for example, that person was maybe just deciding based on how many patients were waiting. So if the queue was too long, maybe he was deciding not to take the BP and make a queue even longer. So decided to randomly skip by tossing a coin whether to record the BP or not record the BP. But it was actually dependent on the number of patients waiting, which to which you will have never an access when you're looking at this data in at a later point in time. Because how many were waiting is not being recorded in the data set. Whether the person was carrying an ID or not is not recorded in the data set. So whenever there is a confounding variable, you kind of what you get, but there is a pattern, you call it missing not at random. If that pattern is visible, you call it missing at random. If there is no confounder, then you call it missing completely at random. And these kind of issues cause a lot of problem, especially when you're talking of prognosis. Now, there are few things you can do uh, because of the challenges this missing data throws, as I was telling you, because we will never know the confounders and never know whether the data is really missing at random. So you know what you get is what you get. You have got the data. You don't know whether it is completely missing at random or missing at random or not missing at random. So you should do some kind of statistical analysis, and that's whole the field of causal inferencing is basically works on this premise that you have observational data, and from the observational data, without knowing where the missing data is, can you establish some kind of causal relationships? But there is something else that you can do, which is typically called in biostatistics as complete case analysis, which is basically you ignore all the missing data and you take all the completely available data and you do a full complete case analysis. Now, this may be good, may be bad, because what if your data set has a lot of missing values? So you, let's say if your data set has 50% missing values, or for 50% of patients there are missing values, then you can drop 50% of the data set. So obviously you are losing a lot of information. Remember the example I was talking about when we were dealing the penguins data set exploratory data analysis, and the gender information was not available for a few patients, for a few penguin individuals. And what we did was we tried to fill that value in. We could have easily dropped those nine, if I recall right, nine were the individuals, right? So we could have easily dropped that data. If you drop that data and then do an exploratory data analysis, that would have been called a complete case analysis. But what we decided to do was the next thing, which is imputation, which is a way of not dropping the data, but filling it with some representative values. And there are again mechanisms by which you can decide which value you are going to replace it with. Now, the coming back to the question about, and let me read the question if I just got it right correctly. How do we time or even test when the event is not even seen? Yeah. And that leads us actually naturally to the next question on survival models. So the idea is you build prognosis model to predict. Uh, okay, so let me build it. So, so models where we, as I've written here, models where we care about the time to occurrence of an event, such as time to 10-year cardiovascular event, for example, or time from treatment to recurrence, or from time from diagnosis to death. I mean, anything. That's what we were doing till now in terms of prognosis models, and assuming we put a neural network, had lots of data, we built a model and kind of did predictions, did everything, evaluation and all that. So prognosis models basically talk about the probability of an event in certain amount of time. Let's say probability of death in 5 years, or probability of recurrence in 6 months, or probability of a cardiovascular event occurring in next 10 years. It's often the metric that is used in cardiology. Survival models take this notion to the next level, and they actually talk about probability of survival past any time t. And this is where the question naturally, I think, leads to. We are not necessarily saying what is the probability of an event occurring in a particular time, but we are saying is will the patient survive after particular time t, and what is the probability of that. So earlier when we were building these prognosis models, we could have, if we had to do a different time zone, for example, if we had to change from 5 years to 6 months or whatever, we have to rebuild the model because they are not designed for different time frames. Survival models actually can answer those kind of questions easily. And what you do is what is called as censoring. And this is the actual precise answer for your question. So we may not see the event happening for many reasons. And what could be those reasons? It could be possible that the patient was attended in a particular hospital and maybe that clinic shut down. So after, let's say, a year of the treatment, diagnosis, and whatever, the clinic shut down and simply the data collection stopped from that center. So you have no more data from that center again. It is possible. Secondly, it is possible that the patient just decided to not report his or her status to the center because everything was fine. We do this many times, right? I mean, you start taking you start a course for hypertension, for example, for treating hypertension. You start taking the tablets, and then everything seems normal, and then you refuse to go back to the doctor or report to the doctor as to what's happening for years on hand. So you, just because you things are fine with you, you may, as a patient, not choose to report your status. And there is a possibility that the patient might have actually had an event, but the family forgot to report it to the clinic. So while the event occurred, the clinic which is maintaining the records doesn't know whether the event happened or not. So all possibilities exist in real life. So this is the data that is what is called as censoring data. And what is called as right censoring is when when you look at a time axis which starts from the left and goes to the right, that's the concept of right here. So when you say right censoring, we are talking about an event always happens after the last contact. So now it's possible that your study may have ended. So suppose you were observing a particular population for, let's say, 3 years, and they were diagnosed. Some of the patients were diagnosed and treated or whatever. And after 3 years, you just don't have data because you're not following them. You're not tracking them yourself. So that's the data, which means at the boundary of the third year, you have to right censor this data because the event has not happened yet. It does not mean it has actually not happened or not, but as per your records, it has not happened yet. Or it could be because of loss to follow up, as I told you, where the patient or the clinic both may be guilty party of not tracking the progress. So survival models is a way, and survival modeling is again another field by itself, which can take 5 weekends if I were to talk to, but I'm just giving you an overview here. So survival data itself may kind of give you uh, a way of estimating this kind of stuff. And then there is the third thing that is often talked about. So we started from diagnostics, moved on to um, prognosis, then on to survival, and the next thing is hazard. And that's a term which is often used. So survival functions, as I told you, we are trying to find the probability of an event happening past that time, past particular time. So we are basically saying what is the probability of survival past 10 years, past 5 years, past 6 months, or whatever. Hazard functions actually answer the different question. They answer the question of what is the patient's immediate risk of event. Death is an example here. What is the patient's immediate risk of an event if they make it to time t? So for example, you had a let's say a patient who had a surgery. You know that patient is going to so you start watching if the patient is going to have a cardiac event in the next 10 years. So 10 years pass, the event has not happened. You observed him or her also. The event has not happened. Now hazard is a way of computing, now that we have passed 10 years from the event, what is the risk, immediate risk for this patient of that event? What's the hazard to uh, that event? And that's another thing which kind of can be estimated, computed, modeled using machine learning. So that's on the side of prognosis. I didn't want to go beyond this, giving this short overview. I also want to talk the third phase, which is the phase of medical treatments, and again, not very in great details. In fact, this will be very cursory level, but I'll give you an overview of what I'm trying to say. So you basically, let's say, give two treatments, and this is how randomized controlled trials are conducted. You've heard randomized controlled trials a lot these days uh, because of mechanisms to establish efficacies of vaccines with relation to COVID-19. So the term has been in use a lot. But RCT is the basic premise of RCT is you have a cohort of to whom you give the treatment, and then there is a cohort which is called the placebo arm or the control arm, uh, to whom the standard of care is given, which essentially means the treatment is not given to them. And then you kind of observe the responses within these two different populations, and then establish whether the treatment this the that you're giving through this drug is actually working or not working. That's essentially the way of conducting randomized control trials. Now, how do you estimate treatment effects? And that's essentially the part of a lot of work which happens in the part of medical treatment that I'm talking about. So you give a drug, and let's say in the treatment arm, 2% get a heart attack in 1 year's time. So that means 1 year later, we are observing this. And let's say in the control arm, 5% get a heart attack. So does this mean that this drug has worked or has not worked? So the way you estimate this is using what is called as absolute risk. So to establish the absolute risk, because this was 2%, you say the absolute risk is 0.02, and it was 0.05 for this group. And that's what is called as a treatment effect. And then you also compute what is called as an absolute risk reduction. And you say that if you give this drug, then there is a 0.03 uh, ARR, which essentially means that the drug does seem to have worked. Now, the problem is, how do you estimate these treatment effects? Because every time you may or may not be able to run a randomized control trial. Well, randomized control trial is the statistical silver bullet, but which is very costly. In fact, you will be surprised that machine learning is now being used to actually design proper randomized control trials themselves. So machine learning can be used for any purpose really, because the assumption is that when we try to set up these RCTs, there is a personal bias, individual subjective bias that can get into it. So machine learning algorithms are actually there are startups. There is a company in US which actually does this, which just designs randomized control trials for many hospitals using machine learning. So there are few things that are estimated. One is what you compute is what is called an average treatment effect versus the uh, what is called as a conditional average treatment effect, which is at an individual level. Now, average treatment effect, remember in RCT, I was talking to you about we have two groups of patients. One is two cohorts, if you will. One is the placebo arm and the another is the treatment arm. And then you kind of average out the treatment effects and compute them at a population level. Uh, so that is one number that you report whether drug was working or not, like the ARR I showed you before. Conditional average treatment is something which you can talk at an individual level, at a patient level. And then there are machine learning models that have been designed, which can actually take this conditional average treatment effect and build a model which can give you uh, the population level average treatment effect, because average treatment effect is difficult to compute because you may or may not have the data. Individualized observations are possible. So there is a case for here for machine learning to step in and to kind of estimate this kind of treatment effects. There are many models. One is called as two model learner, and that's why it's called T learner. T stands for two, and there is a single model learner which stands for S. Now the difference is two model learner essentially means you have these two arms that I talked about, the placebo and treatment. So you build one machine learning model on the patients who are from one subpopulation and one model from the other population, and then combine them in some form to get the average treatment effect. Or you kind of combine them together into one model and build one particular model. And what model could that be? It could be any of the machine learning models that we have spoken till now. It could be random forest, it could be SVM, it could be XGBoost, or literally anything else. I obviously don't have time to go into the details of this, and which is why I said even if we are talking about average treatment effects and things like that, this itself could be a 5-weekend workshop that we could do. So there's a lot of stuff that happens, but I just wanted to give you an overview as to where all machine learning can play a role in healthcare as we go past the diagnosis phase and get into prognosis and treatment phases also. The possibilities are endless. So now I think we are in the last 15 minutes, so maybe I will just start wrapping up. And a few things I want to kind of mention. I have about 10 slides, so I'll try to go fast. But what we have done is we started off uh, and looked at the space at 4 different levels. One is purely from machine learning algorithms point of view, when we talked about regression, classification, and how to evaluate using confusion metrics, ROC, and that stuff. Second was when we looked at the whole thing as deep learning, where you're building the architecture as something which mimics the way human visual cortex works, and try to build a network which can take different data sets and solve different problems, but the architectures kind of remain same. We talked of MLP, convolutional networks, RNNs, LSTMs, autoencoders in that part. We also looked at this space from the healthcare point of view, where you kind of look at the what kind of data you get. I mean, are you working with imaging data, in which case you might use, if you're using deep learning, you might use convolutional neural networks, or you might use tabular data, or you may be even working with genomic data. And the problem that I was trying to kind of bring out as the confounding problem, if I may, in this whole thing is this problem of data sets. No, not enough attention is given to data sets curation and cleaning the data sets, especially in healthcare, and that can actually have significant effect on the outcomes that you have. So knowing algorithms is one thing, knowing statistics is one thing, putting them to reality is another. You look at prognosis and treatment effect computation issues when you may have lots of missing data. How do you deal with those problems? Machine learning does have a lot of role to play in those aspects as well. I don't know if you recall this, but this is a tree-based view I had shown of machine learning algorithms the very first weekend on 3rd or 4th July. And I had said the ones that are marked as the diamonds are the algorithms we are going to cover. And I think we have pretty much covered all of them. So you now roughly know the field of machine learning and deep learning, what kind of algorithms it comprises of, and how you can kind of use scikit-learn library and many other libraries in Python. Although we didn't go through them individually, but I've shared the notebook. So if anybody is curious, can start off on that journey themselves. And this is part where my wrap-up part really is. The things that I want you to remember as you kind of take this learning into your respective domains and disciplines that you're working in, the important considerations are we talk of data science and we talk of statistics, but data science is just a means towards the end. It's not the end in itself. It shows what was formerly invisible is possible. It provides capability and insights, but what it does, it confers power to you. Now your careers will be kind of linked to how you use that power. You can use it uh, well to solve problems at hand for society to make a better society. You will use data science in a positive way. If you use it in a destructive manner, you will use it in a negative way. The choice is always going to be at the hands of individuals who kind of shape this field. The analogy I got this from one of the keynote addresses that was given in one of the US universities, the incoming address that was given, and I found this very interesting analogy. George Kennan, who was the American diplomat, uh, he wrote of Robert Oppenheimer, who led the efforts to build the atomic bomb. He said the recent conquest of power over nature out of all proportion to model strength. So the then scientists were not just among equations; they were not just doing the stuff physics-wise or quantum mechanics-wise, but they faced moral quandaries also. They were wondering whether atomic bomb was indeed a good way to do it or not. Their actions gave power to create and destroy. And I think data science is also at a similar juncture, if I'm not wrong. Let's not be those destroyers who have the capability to kind of ruin the fields. We have seen some negative work happen in CRISPR and those kind of related technologies in gene cloning and gene editing. We hope that kind of stuff doesn't happen much on data science side. Applications are obviously many and varied. I just have been talking only about the healthcare side, but there are applications of uh, machine learning and deep learning to humanities, to social sciences, to life sciences, to physical sciences, and each one of them can be actually a lifetime of learning. So there is so much to do. The difference I see with data science versus traditional science is in traditional science, we get better with experience. We do more and more experience. Doctors accumulate knowledge over a period of time. And for wisdom, you need someone who is very senior. With data science, what has happened is we get better from every interaction with the data set or the algorithms or the setup that you have. Google gets smarter with every search. Pinterest gets smarter with every search. So data science actually gives you the results then and there. Your wisdom is right away there. Health and healthcare also seem to be very poised in the same manner. And that leads us to the issues of bias and fairness in algorithms, which is what I was telling you in terms of whether you're using it positively or negatively is something in your hands. It is in your hands to at least make an effort to figure out whether there is an algorithmic bias in your uh, model that you're building. I showed you the example of mimic data yesterday where majority of the data comes from the white race. So is it fair to use that data and apply those learnings to people of darker skin? The question I asked yesterday, we don't know. Do we need a different data set? Possibly yes. But getting data set comes with a cost, both in terms of money and time. Who's going to invest in that is an answer that we need to do. So I would urge you to kind of take a look at Algorithmic Justice League. Something you can just Google for this, and there's a whole movement which has started, which is now focusing on ensuring that the algorithms that we design are not don't have an inherent bias and are trying to be as fair as they can be. And if they are unfair, then there must be ways by which rights and responsibilities be established, accountability established, so that people uh, can have answers on this. And I can go on the social justice part on this side a lot, but I would rather not go on that path as an example. So the typical ML workflow, again, one of the slides I showed you on the first day is what you do. And some of the things that also became very evident through some of the 4 or 5 notebooks I showed you is this whole process that you start with a problem definition and go back through iterations every time. There is a feedback at every possible time. And there is no one model that answers all questions in the world. There is a model which answers the questions for the given data set at a given point in time. If the data set evolves in 6 months' time, then you also ensure that if the data set also matures or increases or enhances, then you also ensure that your model needs to be reevaluated again. So there has to be a continual assessment of the algorithm at all times. It's not like a job once done, forgotten. I'm giving some links of some of the resources that you may like if you are interested in to further pursue machine learning in healthcare. Please go and explore each one of them. They're very nice courses or websites. So in summary now, I think as I come to the winding down part, actually I have a couple of slides more. I want to talk about two experiences, two very interesting examples. And this was a paper called Effect of a Comprehensive Deep Learning Model on the Accuracy of Chest X-ray Interpretation by Radiologists, a retrospective multi-reader multi-case study. This was a study which was published by a bunch of doctors in the Lancet in on July 1st, last month. And what was interesting is I'll add the link to the paper also here before I upload these slides. But what was interesting was the results. So what they figured out was that if you just look at radiologists alone to interpret chest X-rays, they kind of get to an AUC of AUC is the area under the ROC curve to an area AUC of about 0.713. If you look at it as radiologist plus AI, it kind of improves to 0.808. It's a little better. But if you leave it to AI alone, you can actually get an AUC which is very high, 0.957. So does it mean, and this is a question I was kind of asking somewhere in the middle of our course, was does it mean that we should take this result on the face value and say that we should not involve radiologists into the task of chest X-ray interpretation at all and just leave it to AI alone because it gives obviously the best AUC? And I would say the answer is no. I mean, I would say the answer is no in the sense it's not like a universal answer. It's my opinion, but this is something which should start a debate or some kind of brainstorming of thought process inside you, that just because an AI model does better doesn't necessarily mean it is the best way to do it. It is okay if we can pull down the AUC from 0.95 to zero point 0.8 by involving a human in the loop. Whenever we are talking of healthcare and trying to solve any problem in healthcare, or especially those small problems where they become part of a larger clinical workflow, it is important that there is a human involved in the loop, and nothing is left to the AI completely by itself. Howsoever great that AI be, for example, here it is giving you an AUC of 0.9595. It is always better to have a human in the loop, which improves the. So clearly, AI brings an advantage because if you compare this against radiologists by themselves, you are getting a performance which is better. But it is better to have the human in the loop rather than leave it to the AI completely. And it's a very thought-provoking paper which was published last month. I would urge you to read it and see if it kind of incites you to kind of start thinking in some direction. And there is another study that I want to talk about, which was also published in a couple of months ago, maybe April, I think. And the question is very simple, right? You have an X-ray or a CT scan, and the task is to detect if the patient has COVID-19 or not. Sounds doable, right? I mean, diagnosis, medical diagnosis, we spent 5 weekends on this. So what this paper did, there was a study that was conducted in Cambridge, and they measured this till March, till December 31st, 2020. They looked at 415 machine learning papers that were published in the area, and they figured out that not a single one of them was capable of being put to clinical use. In fact, this study actually, I'm giving you here the statistics that they actually reviewed 2,212 papers, which they shortlisted down to 415 after initial screening. 62 of them they decided to choose for detailed analysis and eventually figured out that none of them was good enough to be put to clinical use. And there is a story in that again. The story is that machine learning might look glamorous and everything, but does it actually solve the problem or not? We don't know. Whether the algorithms that we design are fit enough to be deployed in a hospital setup, in a clinical setup, we don't know. Uh, so this is a very compelling result. So it's not enough to just publish a result and about doing something in machine learning in healthcare. See if you are actually making a significant difference to this. That's it. I think I've timed my presentation pretty well. So about a couple of minutes to go. Thank you everyone for being around all these 5 weekends. It was a long commitment. Uh, Weekend afternoons, which can be better spent just relaxing or going out somewhere. Yes, pandemic has put us into some tight spots, so not everybody travels a lot. But despite all that, despite your other commitments, despite your home commitments, you kind of chose to come here regularly and be a part of this journey. It was great fun for me uh, doing it this way. As I told you, I have different thoughts now. I'm kind of thinking of putting this together in some kind of a book form so that we can kind of keep updating the contents over a period of time and then maybe continue to have the conversations in an offline mode. And as I said before, who knows? We may again reconvene for another session, maybe later. But for now, this series winds down. Thank you everyone for again being here and encouraging me to be on time and being punctual. It's been great fun. Thank you, and hopefully we'll be in touch. Thanks a lot. Bye.